All right, so here is our team's presentation, and we just want to thank SciAm, MathWorks, and our school for giving us the opportunity to present today. So we are going to begin by having our teammate Dani McDonald present part one.
Thank you, Julia. Next slide, please. Getting into the problem, we were asked to devise a model to predict the cost per unit bandwidth in the United States, in US dollars per megabits per second over the next 10 years for consumers in both the United States and the UK. So we began by developing a list of prevailing assumptions. The first assumption being that Moore's law will govern hardware development, and the second assumption being that hardware development is the primary factor in improving broadband speed. So what is Moore's law? Well, Moore's law posits that hardware improvements will double the speed and other capabilities of modern digital devices every 2 years. So given these assumptions, if broadband prices remain constant in inflation-adjusted dollars, then we can fit an exponential regression model. Next slide, please. And that exponential regression model is given by this equation and these variables. Next slide, please. To construct the model, we found data from the United States that was aggregate by year and adjusted for inflation. We then ran a simple linear regression where the y-axis is the log price of the megabits per second, where we took log base E of the prices, and the year, which is the x-axis, which starts in 1998 and goes to 2015 according to the data we found. And as you can see, there are points that lie above and below the regression line, but ultimately the regression line is a good fit. Next slide, please. And this is validated by our relatively high R-squared value, 0.9961, which entails that the sum of the residuals is negligible. Next slide, please. So on the left-hand side, we have an exponential regression that we constructed in R post-paper as a method of validating what we found in our paper using Excel. And as you can see, again, the points lie above and below the line and sometimes on the line. And our predictions for the next 10 years are denoted by the pink dots. Next slide, please. So getting into our actual results, you can see that as time proceeds, the price dwindles considerably, almost by a factor of 100. But it doesn't quite reach zero. And the reason for that is the exponential model suggests that it will never reach zero. The asymptotic behavior, it won't reach zero. Next slide, please. Getting into the strengths and weaknesses, we have a high R-squared value, which explains a large percentage of the price variation. And then if we observe the regression line, there doesn't seem to be much random error. As I mentioned earlier, the sum of the residuals is negligible. However, one of the weaknesses is that the data we found is sparse and it's already been aggregated. So if we had found data that, say, wouldn't have been aggregated, we would expect a lower R-squared value. But that being said, we can still predict it using the exponential regression model. Now we're going to get into part two with Julia. Thank you.
All right, so in part two, we were asked to find the minimum amount of bandwidth that's enough to fulfill any given household's needs 90% of the time and 99% of the time. And we were given 3 hypothetical households shown below as our test cases with individuals at different ages, different jobs, etc. So in looking at this, we found that there's 2 main factors affecting households' bandwidth use. One is the number of users. Basically, if there's more people simultaneously using the internet, they're going to use more bandwidth. And second of all, there's the type of usage. So some uses, like streaming HD video, are going to use more bandwidth than, say, checking email. Thus, we concluded that a household's need for bandwidth on any given day is going to be the moment in time with their maximum bandwidth usage. And thus, the household's need for bandwidth over the course of a year is going to be its bandwidth usage on the day of the year when it's using the most bandwidth. So first, to simplify our model, we assume that when someone's using the internet, they're using it for one of 3 purposes: working, attending school, or engaging in recreation. And FCC data gave us a pretty good picture of the average amount of bandwidth each of these 3 activities and subtypes of recreation uses. And so it follows that at any given moment, the amount of bandwidth a household is using is going to be the sum of the number of individuals using bandwidth for each purpose multiplied by the amount of bandwidth required for that purpose. So here's what we did. First, we established 5 different types of individuals. Each individual of the scenarios the problem set gave us falls into one of these 5 categories, and each has their own set schedule for how in any given day they typically use the internet. For example, on a given day, a full-time student's probably going to spend some time using the internet for school, then some time engaging in recreation. And to model a household, we first randomly generated individuals fitting the age and category described in the scenario, but with randomly generated income brackets as well as start times, end times, and lengths for each part of their daily schedule. Then we added each person's internet usage to the overall household schedule. So as you can see in this example, there's some overlap between 8 a.m. and 8 p.m. So usage is likely to be highest at some point then. So we can then determine the time of day when maximum bandwidth is being used and what amount of bandwidth that entails. On the back end, this was accomplished pretty simply with a Python list with 48 indices, one for every half-hour increment in a day, that we just iterate over once for every individual in the household. We then repeat this process for 365 different days for this same household, recording over the course of this year the day with the max amount of bandwidth and the max amount of bandwidth used on that day. Finally, we performed a Monte Carlo simulation using NumPy and Matplotlib for 300 randomly generated households of the given type. So individuals of all the same category and age, but not necessarily the same income bracket or lengths of each part of their schedule. We plotted each household's maximum yearly bandwidth usage in a histogram, which you'll see on our next few slides, allowing us to then determine what the minimum amount of bandwidth that can satisfy respectively 90% and 99% of these hypothetical households. And one more thing is that we were able to model each scenario twice, once in the presence of COVID and once not in the presence of COVID. With COVID, we assume that all school and work takes place at home and thus contributes to bandwidth usage, whereas it does not without COVID-19 because you're not using your own home's bandwidth. As well, we also used recreation times and types data for 2020 for COVID-19 and for 2019 for the absence of COVID-19. I'm going to hand it over to Grace, who's going to go into our results.
So here are our results from the Monte Carlo simulation. And in the scenario 1 household, we were given the prompt. We noticed that the 90th percentile bandwidth requirement was less for pre-COVID, the right-hand graph, than post-COVID conditions, which is the left-hand graph. However, the 99th percentile requirement was greater for pre-COVID than post-COVID conditions. We attributed this disparity to how the average person used less online recreation pre-COVID, but upper income brackets tended to use more, which was shown in our online recreation data. We also notice here that the unimodal distribution under COVID conditions becomes bimodal in non-COVID conditions. This is because school and work, the two main activities that transitioned to online after the pandemic, require the same bandwidth across income brackets. But when you take school and work out of the equation, there's a major difference in low and high income use of online recreation. And now let's move on to scenario 2. So we see here a very similar situation as we saw with scenario 1 with the unimodal distribution for COVID and bimodal for non-COVID conditions. And now let's look at our final scenario. Here we definitely see different results than what we saw in our other two scenarios. Firstly, the pre-COVID bandwidth requirements here were much less than post-COVID requirements. And we attributed this to how all members of this household are both attending school and working. So the vast majority of their bandwidth usage after COVID was because of their school and work needs. Additionally, the bimodal distribution we saw for non-COVID conditions for the last two scenarios is not seen here because those bimodal distributions could be attributed to our online recreation data. And the members of this household are spending a majority of their time at school or work, leaving little time for online recreation. Next slide. And our model was overall a modular, robust model that gets the job done. But if we were to continue this in the future, we would consider weekends and find more data for our bandwidth usage distributions. And now we'll move on to part 3 with Uday starting it off.
Okay, for part 3, we define the problem as finding the most optimal positioning of cellular towers in each region by taking into account population density, motorway proximity, elevation, and conservation lands. We then evaluated this model on 3 cities in the United States. For this presentation, however, we show you the results for one of those cities, Tampa, Florida. We had 3 main assumptions for our model. The first assumption is that the signal strength within the operating radius is the same for our second part of the model. However, this weak signal disparity should be minimized because our first part of the model does take elevation into account. Our second assumption was that different cities have different magnitude of traffic. Thus, we developed a weight for motorway proximity and population density to keep this into account. Our third assumption was that no towers exist in any of the areas we consider. So we assumed that we are the first people to plan the placement of towers in this city. We had to do this because there were no reliable data available for towers already present for the cities we chose. Okay, so getting into the first part of the model, we performed the raster analysis on real-life maps, which we got from ArcGIS. So we had 4 different layers of map. Each of these layers were converted from something made for human viewing to something a human computer can understand. Thus, we created a raster using OpenCV and pillow libraries in Python and made a score range for each of these layers of data. And you can see those score ranges here. And you can also see what rasters are supposed to look like in the 2 images shown. We For later of the presentation, we call each square grid in our raster a cell. Then for each of these cells in the raster, we combine the population density and the motorway proximity score times their weight, while completely disregarding the conservation areas to get our preliminary score. Then our first algorithm looks at combining the preliminary score of the adjacent cells times the elevation weight, which was 0 if the adjacent cell was at a higher elevation than the current cell being processed, and adding that to the preliminary score of the cell currently being processed. We did this to every single cell in our raster to get the final score. Our second algorithm was a little more complex. For each cell being processed, we created these cumulative decaying weighted horizontal, vertical, and diagonal rays pointing outwards from the cell being processed and traveling until a higher elevation area was reached. Next slide, please. Yes. So here you can see the result for Tampa, Florida. The left represents the input data layers we got from ArcGIS. The middle one represents the raster that were created for each of the layers through our Python program. And then the third column represents the results from the two algorithms, where higher brightness represents a more optimal placement. Additionally, the completely black areas represent the conservation areas where towers cannot be placed. For our second part of the model, we use the first algorithm's result.
All right, thank you, Uday. So the next part of the model focuses on actually positioning the towers, and we do this using the radial coverage convergence algorithm. So next slide. All right, so originally we had to develop a model that produces an optimal plan for distributing cellular nodes in a given region. Thanks to Uday's code and raster analysis, we can change that and say that given a 2D array of positive scores, we just need to determine the positions that maximize the coverage of those scores in the best order using overlays of circles. And as seen later, the positive score clause will be necessary. So next slide, please. All right, so the idea is pretty simple and intuitive. So for a given raster, we're going to pass a convolution filter to consider the surrounding cells. And we're going to locate the immediate maximum in the convolved map and mark that position as a placement for the tower. And we're going to delete the surrounding scores in the base raster so we don't consider the region again. We're going to continue this process until the desired convergence is reached. So next slide. All right, for our convolution, we're going to be using a special kernel. It's going to be a square matrix of zeros and ones assigned in such a way that the ones create a circular mask to simulate a tower. Different kernels are going to be considered later in the discussion, but for now we're going to be using this kernel. Next slide, please. All right, so let's go through an example using Tampa. So of course, we're going to pass a convolution for the first step. And as you see, there's two regions where the algorithm may find a maximum. And we're going to be using a radius of 10 because Uday's raster has a resolution of a ½ mile by ½ mile. And a 4G tower has an average of a 5-mile range. So next slide, please. All right, and of course, we have to locate the maximum. So as you see, the algorithm had located it in the center as we would expect. And it's going to delete the surrounding scores to make sure we don't consider it again. So next slide. And then this process is going to continue until we reach a convergence. So in this case, it's going to be 99%. So at the bottom, you see the first couple of steps after in the algorithm. So if you continue, next slide. And then these are the final images in the algorithm. So as you see, once we reach 99% convergence, it's going to stop and it's kind of eating away at the map in the process. So next slide. So at the end of the algorithm, you should see a table of most important towers to least important towers. And of course, you have the positions so you can back reference to a map and place a tower in that given cell. So next slide, please. So a few interesting analytics that you might want to look at is the individual tower coverage. And as you see, is decreasing monotonically, which we would expect from a maximizing greedy algorithm. And on the right, we have the cumulative coverage, which demonstrates the law of diminishing returns. So for Tampa, at about 8 towers, you might see a lower return on investment for the region. So next slide, please. And here's the visual result. In the prompt, we were given 3 regions that we needed to do. So we did New York, Chicago, and Tampa. So next slide. And just to end it off, we might want to consider a few issues with the model. So impacts of anomaly points, how do those affect the model? Maybe different types of kernels. So Gaussian kernel may simulate a signal drop-off a bit better. Maybe raster masking to encourage some regions or discourage others. And maybe have some fun and see what edge cases we can come up with. So maybe not practical, but fun to look at nonetheless. Empirical evidence is always really good, but mathematical proofs are desired. Next slide, please. So with that said, thank you so much for inviting us to present, and we're looking forward to your questions and comments.
Thank you all for the great presentation. So we will get into questions, but before we do, let's just give our students a round of applause for that great presentation. Okay, so I'll actually start off with a question. For part 2, you discussed your Monte Carlo simulation. You constructed these random schedules throughout the day. 2 questions about that. So you chose 30-minute increments in those random schedules. I wanted to understand, like, why did you choose 30 minutes, and would the result have changed if, say, a different increment size was used? And then a follow-up question is, you listed one possible limitation of your model was you would have loved to incorporate more data. And I'm just curious to hear your ideas for what more data would have been to make that model.
Sure. So for part 2, starting with the decision to use the 30-minute increments of a day, well, after we tried 15-minute increments, 30-minute increments, and 1-hour increments, and we found, just based on our data and the spread of times which individuals based on our data tend to engage in these 3 types of activities, that 30 minutes was a good balance between not disrupting our results and also making sure our program is able to run given the time limitations. Mm-hmm. So it would be interesting to try to run it with 15 or even 5-minute increments, but I don't believe that that would contribute greatly to the overall results, especially because for a lot of our things, such as work schedules, they tend to be very similar for every individual. Like the vast majority of people have a 40-hour workday. So I believe that definitely interesting to look into, but given the time we had, that 30 minutes was effective. And as for using more detailed data, definitely in finding data, we had to make some estimates based on what we found. For example, like finding, like based on like a graph or based on just data on average school times in one region, we had to extrapolate like the average amount of time all American school children go to school. It would be nice to try to corroborate those data with some other sources just to make sure we're using the right estimates. At the same time, one thing we would like to look more into is changing our model based on the time of year, because obviously based on like work schedules fluctuating over the course of a year, students not being in school during the summer, in a real world scenario, it wouldn't be 100% accurate to have every day's schedule be the same events in the same order. So it would be nice to find out how internet usage fluctuates for the average user from month to month.
Yeah, great. That makes a lot of sense.
Can I just insert a quick question about the simulation?
Sure.
So you said you use the income levels to make decisions. So in each of those 30 minutes, how did that impact the decision, and exactly how did you make a decision what happens in each 30-minute segment?
So income levels, the main thing that affects, according to FCC data, which is actually in the MathWorks provided data set, is that based on income level, people tend to A, engage in internet-based recreation for different amounts of time in their day, and B, engage in different types of recreation. For example, with HD video, like gaming, like more expensive forms of recreation that use more bandwidth are more likely to be used regularly by higher income individuals than lower income individuals. So we use those data points to create an estimate for, on any given day, like how long are you going to be engaging in recreation? It was normally distributed based on an average of your income bracket, as well as what type of recreation are you going to engage in. We made it so that we included weightings so that individuals were more likely to select types of recreation that based on their income bracket, they historically tend to choose.
I want to get in a couple of questions. I didn't write this question, but the people who did write it said they thought it would be a place, that part 3 would be a place to use mapping software. And you guys did that really well. The use of ArcGIS wowed me. That were beautiful results. Congratulations on that. I have 2 questions. One is, how many of you did the programming? We're talking about the software, the technical computing award here. How many of you wrote wrote programs here? How many of you could have written the programs that were in there?
So at least for part 3, that was a combined effort of Uday and Maxim working on that. Part 2, it was mainly me writing the code with also Grace Jiang helping. And part 1 was Dani McDonald and Grace Jiang working on the Excel. And for our post-paper presentation, Dani McDonald did the R.
Okay, where did you learn to do that kind of work? Do you have a class of that kind of programming, or
I can start with this one,
yeah.
I guess. So I mean, I code kind of on my own time as well. So me and Uday are working on an AI project, so we are kind of familiar with that kind of image processing element of that.
Okay, quick answers because we don't have much time. One is, the next question is, suppose there was more time to work on presenting the program. We're going to stick with the 14 hours to do the modeling, but what if you had an extra day to actually work on how you present the program? Would that be valuable?
I believe so,
Oh,
because
geez.
we had different weights for the different cities. For example, we had a weight for proximity of motorway versus population density. So in our actual research paper, we had a lot more images. So if we had one more day, we would have organized all of the code and presented the image with it.
Okay, great job, guys.
I would like to say that I did write the question and I was among the people who wrote the question. And I have to say,
I knew that. Yeah.
We shied a little bit away from giving people maps because I think we weren't confident that every team would be able to do the sorts of coding that you did. And I'm so impressed and I'm so thankful that you were like, we're not doing your regions, we're doing our own because we're going to use real regions. So I found that to be a really big strength. So thank you for doing that. One question that I wanted to ask was the question of multitasking. So I certainly have 2 computers open and I'm looking over at a phone and I'm using more than one machine. Is there any way that you would be able to adjust your models to account for something like multitasking?
I guess we can start with that. So given the nature of image processing, I guess by multitasking, we can also use parallelization using GPUs. So that's kind of an advanced area. But given more time, we can definitely consider, of course, the convolution can be run on GPUs. And even the last part where you have to find the maximum, it's a sequential kind of process, but there's a few modern advancements in AI where you can use attention mechanisms to actually determine the maximums in parallel. So that could be an interesting thing to look into with parallelism there.
And adding to that, since we did raster analysis, we have these compartments, right? So technically the program is very modular. So we could also find the tower placement for the entire of United States if we could find the map for it. So the code can be adjusted for the actual grid size. For example, for our code, we use 0.5 by 0.5 miles grid size, but for the entire USA, we could adjust that so it actually runs in time and we get a result very fast.
So as a computer scientist, I love hearing these. Oh, go ahead, Cleve.
I was going to say, stay in school, go on to college, go on to graduate school, and 5 years from now, 6 years from now, if I'm still around and you want a job at MathWorks, drop me an email.
So I was going to say,
have you.
I really appreciate his answers. That's an incredible offer from Dr. Moeller there. So that's pretty cool. I think Karen were you asking about question 2? So she actually meant for question 2, when you're modeling internet usage and you have different individual, people multitasking. Can you comment on that? But I appreciated the answer, but I think she was going in a different direction.
Yeah, sorry about that. So in incorporating multitasking into a model, that would definitely given the way our model is outlined, that would be something, given more time, that's pretty easy to add, is if we could find data regarding the types of multitasking that individuals are most likely to partake in, like whether people are more likely to check email while watching video, or like play video games while checking email, etc. And then in each individual section of our schedule, maybe like use the percentage of time that individuals are likely to multitask, incorporate that into the schedule. So for, let's say 60% of the time an individual is using the internet according to FCC data, but the other 40% they're also engaging in recreation. Because we have outlined different functions for each type of usage, we can incorporate those as need be.
I think we probably have time for one last question if any judge has a closing question. So I can ask a non-technical question that we've been asking some teams. What was the most challenging part of the challenge? How did that weekend go? How did you organize how you worked? What went well, what was hard?
So I'd say like one thing that went well is we delegated tasks to like everyone. So we had like some people working on part 1, and then like Uday and Maxim were definitely the ones who worked most on part 3, and then also some people working on part 2. So because of that, we were able to like spread out our time, and like there wouldn't be anybody not doing anything during our 14 hours. One thing I'd say that we had a bit difficulty was near the end when we were like putting together the paper, because none of us are super good at LaTeX, like the language. We were having a bit of trouble inserting the images. So that's why on our paper, we ended up just taking screenshots of images and putting them in as like a full image. So that part was a bit messy. And if we like were to do this again, we definitely look more into how to format the paper better. And that was like the main thing that was a bit iffy, was the paper formatting.
Well,
You can never get good at using LaTeX. Everybody has that problem. They've been using it for years.
with respect to the coding and working from different places, how did you share and contribute to your code in a distributed way?
So that was definitely something interesting to overcome. It was really the first year we as a MathWorks team have had to do that. So 2 of us, me and Dani, were working in person together while the other 3 were on Zoom. We were able to, Zoom screen sharing and Jupyter Notebooks are a godsend. We didn't have too much trouble communicating effectively and viewing each other's code. There was definitely some extra effort that had to be taken to make sure we were all on the same page. Everyone knew what step everyone else was on, just coordination. But ultimately, I feel like we were able to delegate different tasks effectively enough to other people and trust in the process and trust that everyone knew what they're doing, that we were able to, despite that limitation, produce the.
That's great. So that wraps up our time. Before we go, I just wanted to thank you all again and remind you that out of the hundreds of teams that participated in the challenge this year, you were a top 3 technical computing team. So all of the judges, not just the ones here, but everyone who read your paper and looked at it through the different rounds was very, very impressed with your work. We're really proud of what you've done. We're looking forward to seeing you at the Word presentation this afternoon. So thank you.
Thank you so much.
Thank you so much.
Good job, guys.
Thank you so
Thank
much.
you all.
Thank you.